Okay, now we'll be having some preamble of, you can say, the next topic, right? This is not our main topic, but basically it will be going, or it will be taking you towards the next topic, right? Of course, we'll not be able to maybe complete it, but I just give you some insights to this topic, which is word embeddings, right? But what is it and why we are looking at it? It is important to place it in the context of our discussion that we have done so far. Okay, so basically, you see, in these 7.5 weeks or 8 weeks, what we have done so far is mostly classification, almost always classification, except for today where we did something other than classification, right? And the model that we have been using, that was simply a CNN, right? Of course, we had some preliminary discussion on ANN, or what is softmax, what is derivative, but that was actually supporting, right? Because if you know backpropagation, ANN, convolution, only then you can tell what is a CNN and how the advanced architectures work. So primarily, if you summarize the contents, other than autoencoder, everything was focused on CNN, right? Now we'll be changing, you can say, our theme of discussion from convolutional neural networks towards recurrent neural network, right? And if you remember the first lecture, we have had a discussion that when we are discussing CNN, so almost always our case study will be images, right? Because of course you can do convolution on other data as well, but convolution can be intuitively understood very easily if you talk of images, right? That if you do convolution, you detect edge. So it is very intuitive. You can actually see the edge detected, so it makes sense to you, right? But since the image is on learning, right? No, sorry, the course is on learning, not on images, right? So now majority of the examples that we'll do in the second part of our, you can say, semester, that is in the subsequent weeks. So we'll be doing some examples from textual data, right? Rather than images, now we'll do some examples for textual data. And since text is a sequential data, when I'm speaking or I'm writing or I'm typing, there's a sequence, there's a dependency, right? If I start with a noun, then there's a verb, then adjective and adverb and so on, right? There's a complete syntax that what will come after what you can say, noun or verb, or whatever should come next, right? So whenever you have sequential data, we don't use convolutional neural networks. We use something else that is called a recurrent neural network, right? But of course, that is not our topic for today. And recurrent neural networks can work on images as well. They can work on text. They can work on speech signal. They can work on your heartbeat sound signal, or any other ECG signal, EEG signal, because all of that is actually sequential data, right? Since we'll be doing most of our examples using textual data, so before we can study recurrent neural networks, we need to understand, or we need to have a mechanism of representing textual data, right? That how do we represent textual data before we can feed it to the network? Because if I have a paragraph, I cannot feed words to our network. I have to convert those words into numbers, because a neural network can accept numbers. Everything has to be eventually in terms of numbers, right? So this topic, word embedding, is actually the whole, you can say, if I give you one liner conclusion, this topic tells you how you can convert word into numbers. This is the whole, you can say, conclusion of this discussion, that we want to convert words into numbers, and word embedding is one of the very useful ways to do that. There are other ways as well, but one of the very effective ways is word embeddings, right? So this whole of the discussion will be revolving around this. Okay, so as I told you, the key concept of this topic is word embeddings. And what is word embedding? Text converted into numbers. Okay, you have a sequence of words that will be converted into a sequence of numbers, and now you have numbers, you can play with them, you can feed them to statistical model like a neural network. Okay. The from the viewpoint of technical discussion, that how it works, again the key theme is can be summarized in a single statement, right? If you remember your school days, so there were different proverbs, right, which we had to memorize. And there was a very famous proverb that a man is known by the company he keeps, right? So we have slightly changed it for this discussion, and we say a word is known by the company it keeps. Okay. And this is the whole theme of word embeddings. Now, what does it mean? I think you must have guessed to some extent that, suppose I give you a word space. Okay, so what are the other, when I show you these words, what are the words that come to your mind, right? Maybe sun, moon, rocket, NASA, right? These are the things that might come to your mind, of course. And whenever we have this word space in an article, so in that article, in the neighboring of this word, it is likely that such terminologies would be present, right? If you are talking about space, it is likely that in that article you will be talking about moon or a rocket or a launcher or NASA or something like that, right? So this is the whole idea. Of course, we'll see the low level details later on, but the whole idea is that a word, the meaning of a word can be inferred by the company it keeps, right? If you know the company of a word, you can tell a lot about that word, right? Okay, so again, some introductory concepts. The first is the motivation, that why do we need word embedding, right? This I already told you, that when you are, what we are doing is statistical learning. We are using a neural network, right? So the learning algorithm cannot directly accept text as an input, right? If this is the bullet, I have to feed this line to neural network. I need to convert it into numbers, and word embedding is one of the ways. Okay, then you can say, okay, there might be other possible ways to do that as well. Yes, there are, right? Commonly, if you have taken a course on NLP or maybe a course on information retrieval, okay, so this is a very common topic because they tell you different techniques to classify text. A very common problem is classification of news articles into different categories like sports, weather, or entertainment, and so on, right? So in those discussion, it is very common to see frequency-based embedding. Okay, now what is frequency-based embedding? That you simply count how many times a word is appearing and then represent that count in some format. Okay. For example, a simplest way is count vector. What is count vector? Suppose I have a vocabulary of all the words. Okay, I have all the words: a, cat, dog, sun, and so on. And in an article, I count, okay, of course, you remove stop words, so I should not write this article, right? Maybe we have only nouns and verbs and adjectives and so on, right? So you see, okay, in this article, how many times cat is appearing? No, dog, no. Sun is 2 times, NASA is 4 times, maybe sky is like 3 times. Okay, so you have this representation that, okay, these are the words which are appearing in this article. And then you can actually guess that, okay, this is likely to be an article related to space sciences or something similar, right? So this is a very simple way of converting, you can say, text into numbers, that you are simply counting how many times the word is appearing, right? Then there's a relatively sophisticated representation, which is TF-IDF, term frequency, inverse document frequency, right? So again, it is very common in IRT and NLP to use it. Okay, I'll not be explaining it, right? If you know it, it is good. Even if you don't know it, just ignore it, right? Because we don't have to do this. I'm only telling you that these are different ways of representing, you can say, text into numbers. Another way is co-occurrence matrix, right? Where you make a matrix like this, where you have words uh, here and you have words here, and you count, okay, this is one word, this is another word, how many times these two words appear together. Okay, similarly, how many times this word appeared with this word. Okay, and you can then normalize this matrix. So this will actually tell you that whenever you see this word, how likely it is that you will see the next word as well, right? So all of these, which I have introduced very briefly, this is because this is not our main theme. These are frequency based embedding, right? Because in these, you see, nothing is learned. You just have to count something and represent that information in some format, right? But we are discussing it that just like we have been learning different things, we want to learn embedding, right? We want a supervised way so that we can effectively convert text into numbers, right? Rather than just counting or representing them by a histogram or a matrix. So technically, we call it prediction-based embedding, right? That we learn something and then we predict the embedding, just like we do classification and we predict something, okay? So there are two very common techniques. We'll be discussing one of those. The first one is GLOVE, Global Vector for Word Representation by Stanford. And the second one is Word to Vector, which is by Google, right? So in our discussion, we'll be taking this as a case study, but you can extend the same discussion to GLOVE as well, right? So as you can see, as the name is suggesting you, when you say word to vector, it means input is a word, right? Like cat, and output is a vector. So you are converting a word into vector, right? But how it is done, we will see in detail in the subsequent discussion. Okay, so you see, so far, what we have been doing, whenever we have to represent something, we are using one hot representation. Okay, lecture number 2, we discussed in detail how one hot representation works. That if you have three classes, so if it's class number 1, you have a vector of 3. So maybe it's an apple, it is like this. If it's an orange, it is like this. If it's a peach, it is like this, and so on, right? So since we had three classes, we had a vector of size 3, and only one, you can say, bit is on and rest everything is 0, right? So this is a very sparse representation. Okay, now when we are talking about words or text, we have a vocabulary, right? And vocabulary normally is of very huge size, right? Even if you are talking about a limited domain like a call center, even then, of course, people will not be talking about cat or dog, but still it will have a relatively limited vocabulary, but still the size of the vocabulary would be very huge, right? So whenever we are solving a text related problem, first we define a vocabulary of words, right? And it is very common that your vocabulary can easily be 10,000 words, right? Means it is very common for many applications that vocabulary size is around 10,000 or even more, right? Now, if you represent it with one hot vectors like this, so you see a very obvious, you can say, drawback which you can notice is that I have a vector of 10,000, right? Because I have 10,000 words in my vocabulary, in which 999 are 0, and there is only a single one. Okay, so it means all of these are 0, but I have to store them, right? So it means this storage is quite inefficient, right? When you see this is a word and this is the representation. When it says 5391, it is actually saying that at position 5391 we have a 1 and rest everything is 0. Okay, this is just a way of representing which is used in the literature, so I have actually used the same convention. Similarly, if it's a word orange, 456 means that this at position 456 you have a 1 and rest everything is 0. Okay, so that we don't have to write it maybe 10,000 values of. Okay, so one obvious drawback is that you see it is very inefficient representation, especially when you are talking about a large vocabulary. But there's a there's a much you can say bigger disadvantage. And what is that? Let's try to discuss that in detail. Suppose we have two sentences. The first sentence is have a good day, and the second sentence is have a great day, right? So the total, okay, this is the whole corpus. Okay, we don't have anything else. So if I have to make a vocabulary, I see, okay, how many words are there, unique words? I have 1, 2, 3, 4, 5. So this is my vocabulary of 5 words. Okay, all the words in my corpus, I just split them and they become my vocabulary. Okay. Now, if you have to represent these words in one hot vector, the size of the vector would be 5 because I have 5 words in the vocabulary. So maybe have is this. This is a, good, great, and day. Okay. Now you see, as a human, when you read these sentences, so you see good and great, they actually are used in the same sense. Okay, means good and great are like similar words. Now the disadvantage is that let me just explain to you the disadvantage. Okay, So now you see you have a vector for good, which is like this, and you have a vector for great, which is like this. Okay, you have a vector for have, which is like this, or so on. Okay, now if this is good, this is great, this is have, and maybe you even have a cat or dog, right? If they are represented by vectors, the relation between good and great is same as the relation between good and have, or good and great and cat, right? It means there is no relation at all. On the other hand, if I say good day or great day, as a human, you can interpret that good and great are actually referring to the same idea, that you are actually liking the day, right? But in this representation, when you try to compute the similarity between two words, you take their dot product. Okay, so if you take the dot product of these two vectors, it is 0. If you take the dot product of good and maybe this vector, this is again 0. So you can take the dot product of any two vectors, it will always be 0, right? Why is it 0? Because you have a 1 at a different position. So whenever you are doing it, it means there is no relation between different words. Every word is independent, which is not good, right? It means that if two words are synonyms, even their dot product would be 0, right? So two words are exact synonyms, good and great. Maybe even some other example that you can think of, but still they do not have anything in common. And why? If I visually draw it, since I cannot draw 5 dimensions, so if I draw only 3 dimensions, okay, suppose this is a word which is book. Okay, it is like 100, so this is your book. Similarly, this is a word called, say, teddy bear or maybe beer, which is 010. And here you have a third word which is, say, soft, which is 001. Okay, now you see you have this one vector, the second vector, and third vector. You take the dot product of any two vectors, it will always be 0. But we know that if you are reading a novel, and if there's a concept of a, say, maybe a stuffed toy, like a bear, then it is expected to be soft. So both of these concepts are somehow related. On the other hand, there is no correlation between a book and a soft, right? But in this representation, everything is treated independently. There is no relation between these words. So that's why when you are dealing with text, will not be using one hot encoding. We'll be using something much better, which is called word embeddings, and that we'll see in the next discussion, right? So let me just conclude this, and maybe we can move to the next thing.